Hello and welcome back for the second part of the Design by Contract overview. In our first installment, you saw that in Eiffel, we can write the specification of a routine, that is, what the routine does, directly in the text of the routine, yet apart from the routine's implementation. And this specification is checkable at runtime, and it defines a contract between the routine and any caller of the routine. Now, if this were still 1975, that might be all we need. Back then, we had only routines. The routine was the unit of software reuse. But for a while now, we've been developing software with object orientation versus functional decomposition. This means that we now construct software systems as sets of related classes. Each class serves as the definition of a data type, and class is our unit of software reuse and modularity. That is, we reuse software, a class at a time, and all usable software text must be part of some class. So in this presentation, we'll expand our contract from the routine to the class. And then we'll take a look at how contracts affect another benefit of object orientation, software reuse through inheritance. And finally, we'll summarize the benefits of design by contract. Remember in part 1, we constructed a routine set hour for class time of day with a specification and one possible implementation. Well, the time of day class could have other routines too, like set minute and set second. Each of those routines would need to be specified as well. So here's set minute. Looks a lot like set hour, but notice that the precondition specifies the proper range for minutes, and the postcondition ensures that after execution, the minute will have the same value as the argument m, and that the hour and second will remain unchanged. So we go on and build the best contracts we can around the routines in a class. Once we've done that, we've almost got a complete contract for the class, but not quite. There's one other type of assertion that can provide another very important element of specification for a class. And this assertion is called the class invariant. It tells us what it means for an instance of the class to be valid. So the class invariant must be true at all times, hence the name. But when we say at all times, we really mean at all critical times. That translates to any time at which the instance is observable by clients. And that translates to before and after the execution of each routine that's publicly available to clients, or as we say in Eiffel terms, routines that are exported. What this implies is that during the execution of an exported routine, or other private routines that the exported routine might call, it's okay for the invariant to become untrue temporarily. But by the time the exported routine completes, the invariant must again be true. Imagine the example of a class modeling a linked list. You might somehow be able to express in the class invariant the rule that one node must be linked to another. Then when you write the insert routine that puts a new node somewhere in the middle of the list, insert has to be able to break the invariant during the time that it's threading in the new node. But by the time it gets done, everything has to comply with the rules again. As you might suspect, there's only one class invariant per class. And in the Eiffel class syntax, it's coded below all the class's feature clauses. All right then, what would the class invariant for our time of day class look like? Well, we know that for any time of day, the values for hour, minute, and second must fall within certain ranges. And if they all do, then we can say that this is a valid time of day. So we express exactly that in the class invariant for the class time of day. At runtime, if ever this invariant becomes untrue for an instance, then an exception occurs. And as with the assertions on routines, the invariant violation exception indicates that the software is not in compliance with its specification, which in turn means that the software contains a bug. One of the most common types of runtime problems in object-oriented software systems occurs when objects become invalid. And without a class invariant, a corrupt object can go unnoticed for some extended period. The corruption of one object causes corruption in other objects, and so on. When some human being finally notices that things aren't right, the violation of the original object may have been so long ago in execution terms that it's really difficult, if possible at all, to trace the source of the problem. But with the class invariant, as soon as the instance becomes invalid, the exception occurs. Bugs are caught early and are clearly traceable. This can make a huge difference in the quality of the software you deliver. Now let's see how this class invariant, teamed with the contracts for all exported routines, gives us a complete contract for the class. Because we reuse software a class at a time, we want to see what services a class makes available to us, and what we need to do to use these services properly. And we get this information from the class's contract view. The contract for a class includes the contracts for each of its exported features. This means the contracts for exported routines and the declarations for exported attributes. The class contract also includes a class invariant. So with the contracts for each of the routines, you see the obligations and benefits for the clients and suppliers. The class invariant adds a definition of object validity for instances of the class. But we can also view it as a general set of constraints to which all actions must comply. In the analogy to human contracts, you could think of the invariant as the law of the land. For example, no matter what gets agreed upon between a builder and his or her client, the builder is not allowed to construct buildings in a fashion that violates the local building code. So now let's look at the contract view for the class time of day. There won't be enough room on this slide to show the whole contract, but here's a kind of a representative sample. As you look at this stuff, bear in mind, as you did with the contract for routines, that the contract is not dependent upon specific implementations. Remember, we discussed two different ways of implementing time of day, and it's important to note that the class's contract does not betray which implementation choice we made. Here's what I mean. In the first part of this contract, we see the features hour, minute, and second that are queries that allow us to ask about specific component values for a time of day. To conserve space here, I've only shown hour. One choice of implementation might cause hour to be an attribute, that is, just stored in memory. A different choice might make hour a function, that is, computed. But because of the principle of uniform access, you can't tell by looking at the contract which choice was made. Hour will look the same as an attribute or function, and the client code won't have to know the difference either. So if the producer of time of day later changed the implementations and released a new version of the class, all existing client code would require no changes to recompile and execute properly. In addition to the queries like hour in the class contract for time of day, we also see the contracts for each procedure that's available to clients. So here's the contract for set hour. And last we see the class invariant, the statement defining the validity of time of day instances. So that's the contract for a class. When you view the Eiffel Studio presentation, you'll see how Eiffel Studio makes this type of view available to you quite easily for any class. And that makes sense because as a reuse consumer, you're always interested first in the specification or contract of a class. That is, what the class can do for you. Now let's consider what effect class contracts have in the presence of inheritance. But before we get into that, let me review a couple of basics here. And if I repeat concepts about which you already have a full understanding, then please just try to bear in mind that repetition is the mother of pedagogy, and forgive my being redundant. Okay, in object orientation, the class is the unit of software reuse. And there are two ways to reuse classes, each based on one of the two possible relationships between classes. One class can reuse another either by becoming a client to that class or by inheriting from the class. So far, we've only considered the client case. Okay, to summarize the client-supplier relationship, here's an example. Some class, like time of day, presents itself to potential reusers through its contract. When another class, like this daily routine class, uses instances of time of day, like coffee time here, the client-supplier relationship is formed. Time of day is a supplier of services to its client, daily routine. When daily routine applies features of time of day to instances of time of day, as in this call to set hour, the semantics are governed by set hour's contract. Okay, so much for contracts and client-supplier. Let's move on to inheritance. In inheritance, rather than building a new class from scratch, we extend or specialize one or more existing classes. EIFEL is unique in its support for full, safe, controllable, multiple inheritance. But for the purposes of this overview of design by contract, we'll consider only single inheritance. When some class, say automobile, inherits from another class, say vehicle, then the features of class vehicle are available automatically as features of class automobile. And any instance of automobile can also be considered an instance of vehicle. Let's look now into how contracts really help us to see the full implications of inheritance. Suppose we were writing a class which could use instances of time of day, as in our client-supplier example. But also suppose that we wanted to use a service on an instance of time of day that was not provided by the time of day class. For example, suppose we wanted a query that would provide the hour nearest the time of day represented by an instance. So if the value of the instance was 8:15, we would want 8 back. But if it was 8:45, we'd want 9 back. So we would end up wishing that the contract for time of day included a query nearest hour like this. And this happens all the time in software development. Portions of a new development are many times simply variations on a theme of some previous development. Well, what options would we have if we needed this functionality? Let's start with some of the more unpalatable ones. If we have the source code for the time of day class, we could copy it with a new class name and write our stuff into it. This was the state-of-the-art in software use in many organizations for a long, long time. In fact, long ago I remember hearing rumors that only one COBOL program had ever really been written from scratch. So the 1.5 gigalines still in existence are all somehow derived from copies of that same first program, likely written by Admiral Hopper herself when she was only a lieutenant commander. Okay, probably not true. But this is an awful way to reuse existing software. It more than doubles the maintenance load. It disconnects the new software from the original producer, just to name a couple of flaws. Option 2 is perhaps more desirable, but less likely to occur. We submit an enhancement request to the producer of time of day asking for the functionality to be added. This might work okay if the producer lives in the next cubicle, but if the class is a product of Megalo Giant Never Change Nothing Software Incorporated, then we better tell our boss that our project's on hold indefinitely. The third option is to do it in the client. So within the client we would add a function, that is a computational query, that would take as an argument a time of day and return the nearest hour derived through computation. Of the three, this option may be the most easily done. It's still pretty awful because even though we haven't talked about what types of objects our client class is modeling, the calculation of the nearest hour for an instance of time of day probably violates the cohesion of the model. It just doesn't belong there. So we've seen three ways of getting the stuff we need, all of which we find objectionable for one reason or another. Now let's find a better way. So we build a better, or at least a richer, time of day class. But we don't do it by copying the old one and hacking it. Instead, we use inheritance to make our new class an heir to time of day. At this point, our class will have the same set of features as time of day. But of course, we want to add a new feature. So we do that. Nearest hour returns an integer that is the hour nearest the time held by an instance of richer time of day. Nearest hour is a function and as such can have its own contract. In this case, just a postcondition that describes the semantics of the computation. Then lastly, we might want to write assertions into the class invariant that ensure that nearest hour always returns the right value. One could argue that this is a bit of duplication, but if we decided later to change the implementation so that nearest hour was an attribute rather than a function, these invariant clauses would be critical to the validity of instances. Well, now we've reused the time of day class through inheritance. Let's look at the effect of time of day's contract on richer time of day. At the most basic level, here's the story on contracts and inheritance. An heir class inherits the contracts of its parents. Each class inherits features from its parents. In doing so, it also inherits any contracts on those features. So a call to set hour on an instance of our richer time of day class must conform to the same contract as a call to set hour on an instance of time of day. Okay, now what about the class invariant? It's inherited as well. So the test for instance validity on an heir is at least the same as on its parents. In the case of class richer time of day, the validity assertions for hour, minute, and second, which were originally defined in the invariant on class time of day, apply to instances of richer time of day too. Now, if you remember, we added the nearest hour feature to class richer time of day, and some invariant clauses as well. Now, what effect does that have on richer time of day's class invariant? Well, here's a portion of class richer time of day showing the nearest hour feature that makes it a little richer class than class time of day. When we added the nearest hour feature, we also coded some class invariant assertion clauses to ensure the validity of nearest hour in the context of the rest of the state of any instance. And we said that richer time of day inherits the class invariant from time of day, so the new clauses coded on richer time of day are added to the clauses inherited from time of day. Now, by added, I mean that in the presence of an inherited contract, these new clauses are logically ANDed together with the invariants of all parent classes to form the invariant for the new class. So class richer time of day has a richer class invariant, one that contains the assertion clauses written directly on the class, plus those inherited from parents. And so it goes on. Any classes which are heirs to richer time of day will inherit this invariant. The specification of these classes, in great part, will come to them through their parents. Well, there's a bit more to this business of how contracts interact with inheritance. But this is about all we have time for in this overview, because I want to take a minute to show you what a profound effect inheritance of contracts has on our ability to reuse software. It would be difficult to overstate the importance that the effect of inheriting contracts has on your ability to reuse software you've already built. Really. In fact, when it comes to getting new systems out the door, this may be the most important difference between Eiffel with design by contract and other methods and languages that don't have it. Let me try to explain. Object orientation allows us to reuse a class in two ways, by writing a client class or by writing an heir class. But in the absence of design by contract, we would tend to favor client-supplier reuse over inheritance. Why? Well, really there are more reasons than one, but certainly the most pressing reason is reliability. If we allow an heir to be created, that heir will necessarily have access to the internal structure of instances. And as such, the code in the heir could manipulate an object's attribute values in such a way that an instance could become invalid. And this is really a big threat to reliability. As I told you before, undetected corruption of objects is one of the most common and nastiest problems in running OO systems. Now, if you want some evidence, just look at how inheritance prevention has been built into other environments. In Java, there's a facility called Final. And in .NET, there's a similar thing called Sealed. What these do is to allow programmers to mark their classes as final or sealed, meaning that no one can create an heir to the classes. Engineers prevent inheritance through these facilities primarily to preserve integrity of objects from misbehaving heirs. Well, you might wonder, how often are these facilities actually used? And it turns out that they're used very often. For example, if you look at the type libraries that are delivered with .NET, you will notice an alarming number of types that are sealed. In some cases, as many as half of the types in the library. So these are all software components which cannot be reused through inheritance. As you can see, even the Java type java.lang.string is final, and the .NET type system.string is sealed. These are the classes we use to model strings of characters. And it doesn't take much imagination to think of an application for a specialization of string of characters. Now, there's no sealed or final facility for Eiffel classes, and single, multiple, and repeated inheritance are used widely throughout the delivered Eiffel class libraries and by Eiffel developers worldwide. Is this simply because Eiffel people are reckless programmers? No, quite to the contrary. We believe that if anything, Eiffel gives us a framework for more responsible development. We use inheritance widely because it is a very efficient way to reuse software, and we can do it safely because we have design by contract. You see, all Air classes must respect the contracts they inherit. So, for example, when we added the nearest hour routine to the class richer time of day, we can't do anything in that routine that violates the integrity of an instance as defined by time of day's class invariant that we inherited. So the contract we inherit prevents us from producing misbehaving heirs, but it doesn't seal off valuable software from reuse through inheritance, as in .NET and Java. Okay, now that I'm done with that hysterical rant, I want to finish up this overview by reviewing the ways in which design by contract helps us produce better software, and as a consequence, lowers our software costs. I hope that during these two design by contract talks you've already recognized some of the obvious benefits. But to help you put things in perspective, think about this. Suppose we look back at our very first try at the set hour procedure in time of day. Remember, it looked like this. Notice that there's no require keyword and no ensure keyword. This will compile and run just as it is. But what does it mean? The require and ensure aren't required. So does that mean that this version of set hour has no contract? You may be surprised to learn that indeed it does have a contract, and the contract looks like this. The precondition and postcondition are, by default, the weakest possible assertions. So what does that mean in terms of the contract? Well, it makes set hour's contract read something like this. There's not really anything in particular that needs to be in place before I do my job, just give me a call. And oh, by the way, you should know that I'm not going to guarantee any particular results when I get done. Now, it's hard to imagine a case in which this would be a useful contract. In most cases, as with set hour, it would be woefully inadequate. But bear in mind that it's the same contract that you specify any time you code a routine and allow the contract to default by omission in Eiffel or in any other language. And because only Eiffel has comprehensive support for DBC, if you're working with something else, you should consider the possibility that you may be walking the high wire without a net. So let's finish things up now by reviewing some of the benefits of this safety net we call design by contract. First of all, DBC gives you built-in correctness. Correct software reduces software cost because it requires little maintenance, and it can be reused with confidence. As we said, correctness is only meaningful if we can specify what software is supposed to do. And in Eiffel, we build the specification and keep it in the code. As a result, the activities of the code are self-checking at runtime and self-debugging. Think about the typical debugging process. Once we know we have a bug, oftentimes it takes us a lot of effort to find it. But design by contract makes our code self-debugging. If a precondition gets violated, then the bug's in the client. A call was made that didn't meet the requirements of the called routine. If a postcondition gets violated, that means that the precondition held, but that the call routine didn't do what it promised to do. So the bug's in the supplier. Likewise, in the case of an invariant violation, during the last call the precondition held and the postcondition was met, but still the routine did something that caused an instance to become invalid. So again, the bug is in the supplier. The Eiffel syntax is simple, concise, and elegant, and it must be because Eiffel the language supports the full life cycle Eiffel software construction methodology. So reading Eiffel is not just a programmer's sport. The contract views built automatically by Eiffel Studio are readable with little training by managers and domain experts as well. Because of design by contract, we have a clear delineation of what's within our software specification. DBC is kind of like tough love for software. Routines are compelled to be responsible for their own actions, out-of-spec situations or bugs, and bugs cause exceptions, and exceptions leave only two options, recovery or failure. But even in failure, routines have an opportunity to demonstrate their robustness by cleaning up their mess, say closing database connections and freeing other system resources and the like. If we can reuse a lot of software that we've already built, then we'll spend less money building new stuff. And we won't be adding mega lines to our maintenance load either. Having design by contract allows us to exploit safely the reuse of software through client-supplier, and in contrast to other environments, through inheritance too. Because descendant classes inherit their ancestors' contracts, as soon as they're born, they have a set of rules with which they must comply. And if they get out of line, we know it immediately. Well, thanks for listening. In this overview, I didn't have time to tell you everything that there is to know about design by contract, but I've covered most of the critical points. I hope you found it informative and thought-provoking. If there are things you didn't quite get on the first time through, you can use the navigation controls on the left to go back and review piece by piece. And if you have any questions about DBC, get in touch with us and we'll try to help you out. We speak from experience when we say that design by contract can have a truly profound positive effect on software quality and cost.